Right now, one object dominates the attention of astronomers across the world. 3I/ATLAS, an interstellar visitor from beyond our solar system, is no longer behaving like the faint blur that early models suggested. Instead, it is doubling in brightness faster than anyone expected. NASA confirms what telescopes have been recording night after night, a surge that has transformed predictions into astonishment. What should have been a flicker on the edge of detectability has become a spectacle. The coma surrounding the hidden nucleus has expanded into a vast green halo, hundreds of thousands of kilometers wide, scattering sunlight across space like a luminous beacon. 6 times brighter than anticipated, Atlas is forcing scientists to rethink everything they thought they knew about this kind of visitor. Its glow is not a gentle rise, but an accelerating curve, a climb that outpaces every projection. Astronomers are now locked in debate, asking what could drive such explosive growth. Is sunlight unlocking alien ices buried deep within the core? Is it a runaway release of volatile gases never before observed in comets from our neighborhood? Or is it something stranger, a process yet to be identified, emerging only because this object was forged in a different star system with chemistry we have never encountered? The answers are not clear, but the urgency is. Every observation logged now becomes a clue, every spectral line a fragment of evidence. NASA's confirmation of the Brightening has sharpened the focus. The data show a body that is not fading into the background but roaring to life, carrying with it the fingerprints of a different world. And as Atlas continues its journey inward, the stage is set for a confrontation between theory and reality. The numbers are staggering. At this moment, 3I/ATLAS is racing at 60 kilometers per second. By the time it swings closer to the Sun, that speed will rise to nearly 68 kilometers per second. To put that into perspective, that velocity is more than twice as fast as any planet in the solar system. It is enough to cross the distance from Earth to the Moon in just over an hour. No spacecraft launched from Earth has ever traveled at such a pace under its own power. This is the speed of a traveler forged in another system, one that has spent millions of years in the dark between stars before plunging into our skies. Brightness is measured on a scale that can feel abstract, but the numbers tell the story. Atlas has now reached magnitude 12. That is invisible to the naked eye, fainter than what even seasoned observers with binoculars could hope to catch. And yet, the surge matters. Compared to what models projected, it is glaringly strong. The coma surrounding the nucleus is not just expanding but reflecting more and more sunlight, creating the illusion of a giant glowing world suspended in the void. With every week, the halo grows wider, scattering light in ways that defy easy categorization. This is not just a matter of brightness on paper. The growth of the coma changes how instruments read the object. It alters the balance of gases detected in its spectrum, reshapes the way tails form, and complicates every attempt to forecast what will happen next. Scientists across observatories in Hawaii, Chile, Arizona, and Spain are logging round-the-clock measurements, each update feeding into models that try to predict where the surge will peak. Yet the light curve is veering away from every projected line. The object is not just active, it is unpredictable, but the opportunity to track it is narrowing quickly. By late October, Earth's view of ATLAS will begin to vanish. The angle between the comet and the Sun, what astronomers call solar elongation, will shrink below 30 degrees by October 21st. That is the threshold where even the largest ground-based telescopes struggle to separate the comet's faint glow from the overwhelming blaze of daylight. For most of the world, the practical viewing window will collapse into a narrow sliver just after sunset, with the comet barely clearing the horizon before sinking into the haze. Amateur astronomers are racing against time. Some gather in online forums, coordinating observation relays across continents, handing off the comet from one longitude to another to squeeze every possible image before the blackout. Others report failed attempts, their telescopes overwhelmed by twilight, while a handful capture rare successes that spread across networks within hours. It is a chase against geometry itself, a scramble to preserve a record before the Earth-Sun alignment closes the door. Professional observatories bound by strict safety protocols are already stepping back. Pointing million-dollar optics too close to the Sun risks permanent damage. Instruments that might capture faint emissions cannot take the chance of stray light. One by one, they retreat, leaving only amateurs and automated surveys to collect the last fragments of data. And when the Sun finally swallows the comet from Earth's perspective, there will be silence. No direct measurements, no spectra, no images. A complete blackout just as Atlas reaches the peak of its activity. The blackout, however, does not end the story. It shifts it. For once, Earth is not the only vantage point. Mars, for a brief window, becomes the frontline outpost for humanity's effort to study an interstellar object up close. On October 3rd, three I/ATLAS will sweep within about 28 million kilometers of the red planet, close enough for orbiters to aim their instruments, far enough to avoid any dust hazards. The geometry is perfect. While Earth's view fades, Mars's view opens wide. A fleet of orbiters is already preparing. The European Space Agency's Mars Express, with its high-resolution stereo camera and spectrometer suite, will attempt to capture both images and chemical fingerprints from millions of kilometers away. The ExoMars Trace Gas Orbiter, equipped with instruments designed to sniff faint molecules in the Martian atmosphere, will instead aim them outward, searching for exotic volatiles streaming off the comet. NASA's MAVEN mission, usually focused on the plasma environment of Mars, will tune its ultraviolet spectrograph to track the glow of Atlas's gases, while its plasma sensors monitor how the solar wind interacts with the interstellar visitor. Even the Mars Reconnaissance Orbiter, famous for its high-rise camera capable of snapping details on the Martian surface, is being enlisted. If conditions align, it might capture the nucleus itself as a distinct point inside the sprawling coma. Tracking a fast-moving comet is a challenge for any spacecraft, but the advantage belongs to Mars. For the first time in history, a planet other than Earth will become the primary observatory for an object not native to the solar system. The urgency is palpable. Instrument teams are running simulations, updating ephemerides, and negotiating observation slots. Bandwidth is limited, pointing constraints are strict, and every minute counts. Each mission wants its share of data. Images of the coma, spectra of the gases, plasma interactions, ultraviolet emissions, all of it is needed to piece together the story. There will be no single uninterrupted coverage, but even fragments could yield insights never before captured. The stage is now split between Earth and Mars. On one side, observers on Earth race against twilight, knowing the window will slam shut. On the other, orbiters circle Mars, primed to collect data that no telescope on Earth can. Atlas is forcing a shift in the very way humanity studies the sky. For once, planetary science and interstellar astronomy meet on the surface of another world, with machines orbiting Mars taking the lead in unraveling a cosmic mystery. Every surge in brightness, every expansion of the coma, every trace of green light carries a message. It is not simply about what 3I/ATLAS is, but about what it represents. A visitor from another star system revealing itself in real time, brighter and stranger than expected. NASA confirms the growth, but the mystery remains unsolved. And with Mars now stepping into the role of primary witness, the pursuit of answers continues. The most striking detail that sets 3I/ATLAS apart from nearly every other comet is its color. To the naked eye, through even powerful instruments, it carries an unmistakable green glow. Spectral analysis has quickly traced this to diatomic carbon, the molecule known as C2. When sunlight hits these carbon-rich molecules, it forces them into an excited state. As they relax, they emit photons in the visible spectrum, and the result is the vibrant green that observers around the world are recording. This is a classic marker of cometary activity, yet the sheer intensity of ATLAS's glow is extraordinary. Even from a distance of 2 astronomical units, the signal is unusually strong, dominating the light curve in ways rarely seen before. The data have not come without disputes. Some teams have flagged possible contributions from ionized carbon monoxide or the cyanogen radical, both of which can produce green or blue emissions under solar ultraviolet light. Calibration differences, background subtraction issues, and regional observing conditions all feed into the disagreements. In scientific forums, arguments play out over how to interpret each spectrum, with rival groups defending their methods. Yet the strongest and cleanest data sets consistently point back to C2 as the main culprit. That conclusion alone carries weight. It implies that Atlas is loaded with volatile compounds rarely found in such abundance in typical comets of our solar system. The green light is more than aesthetic. It is a chemical clock ticking in real time, marking the pace at which fresh ices erupt from the nucleus as solar radiation slams into its surface. Each brightening is another layer of material peeled away, another surge of alien molecules released into the coma. The growth of this green halo is therefore not simply visual spectacle. It is a direct record of surface chemistry under conditions that no laboratory experiment can reproduce. Every photon scattered from ATLAS carries the story of matter forged around another star, now igniting under the heat of our own. As the glow intensifies, another anomaly has begun to appear. Observers in September flagged faint hints of a narrow sunward feature stretching back toward the sun itself. This so-called anti-tail runs against the textbook expectation that cometary dust should be swept outward by solar radiation pressure. To see a feature projecting toward the sun is to see geometry and physics conspiring in unusual ways. And if you want to keep following these rare cosmic surprises as they unfold, make sure you hit that like button and subscribe. It helps us continue tracking every twist in this unfolding story. The explanation rests on ATLAS's extreme speed, combined with its massive coma. Dust grains ejected from the nucleus are caught in a tug-of-war between radiation pressure, gravity, and electromagnetic forces. At such high velocities, some grains, particularly larger or electrically charged particles, can move ahead of the comet's path. When Earth's viewing angle happens to align with the plane of the dust sheet, these grains appear as a slender sunward spike. Plasma physicists describe it as the focusing effect of the solar wind colliding with the comet's own outflow, channeling particles into narrow streams that momentarily project in unexpected directions. These features are fleeting. They depend on particle size distributions, solar wind variability, and the constantly shifting geometry of Earth, Sun, and comet. Reports of anti-tails in solar system comets exist, but they are rare. To detect one on an interstellar object at this scale would be extraordinary. For now, confirmation remains tentative. Amateur and professional teams alike have flagged the structure in images, but peer-reviewed measurements have yet to be published. Even without certainty, the possibility adds another layer of intrigue. Atlas continues to defy neat classification, producing features familiar and alien in equal measure. That refusal to fit neatly into established categories has become its hallmark. Consider the comparison to its predecessors. Oumuamua, discovered in 2017, was a dry shard, cigar-shaped, tumbling silently, with no coma and no visible tail. It slipped past almost unnoticed, except for its bizarre shape and trajectory. 2 years later came Borisov, the second confirmed interstellar visitor. Unlike Oumuamua, Borisov resembled a classic comet, with a bright coma dominated by water vapor and cyanide, and a tail that behaved as models predicted. Together, those two objects framed the boundaries of what astronomers expected from interstellar arrivals. Atlas refuses to stay inside that frame. Its coma is not just large but oversized, rivaling the diameter of Jupiter. Its green hue from C2 is not just present but overpowering. Its brightness surge is not gradual but explosive, outpacing every prediction. And now it hints at an anti-tail, a feature almost unheard of in interstellar bodies. In short, ATLAS is not Oumuamua, and it is not Borisov. It is something else entirely. By resisting easy classification, it forces astronomers to question the very definitions of comets, asteroids, and interstellar wanderers. The labels blur, and new categories must be imagined. The contrast highlights the scientific stakes. Each interstellar visitor is rare, separated by years of waiting. Each carries chemistry and physics from another stellar nursery, fragments of worlds beyond. Oumuamua showed dryness and tumbling complexity. Borisov demonstrated water-driven outgassing much like homegrown comets. Atlas is rewriting the playbook with its brightness, its chemistry, and its evolving morphology. For planetary science, this is not just curiosity. It is data that will reshape models of how matter forms around distant stars. All of this builds toward a single date, October 29th, when Atlas reaches perihelion. The close pass will bring it just inside the orbit of Mars. Models suggest that after that point, it will begin to fade, perhaps rapidly, as it speeds away from the sun. The coma will shrink, the green light will dim, and the object will retreat into the dark. Yet the race before perihelion is far from over. Every day counts. Citizen science groups are at the heart of this chase. Across Discord servers, forums, and shared pipelines, amateurs and professionals exchange updates in near real time. Light curves are posted within hours of observations. Spectral anomalies are flagged and debated. Digital images are stacked and processed to capture faint features that single exposures cannot reveal. For many participants, this is the first time an interstellar visitor is being chronicled so openly, with data flowing from backyards as well as from billion-dollar observatories.